What's going on, guys? Today we will analyze the risen ransomware and perform a full reverse engineering to understand its code logic. We will also solve a practical scenario from LetsDefend and answer the challenge questions.
The sample we're going to analyze today is called the Ryzen sample or the Ryzen ransomware. Now, the thing is about this ransomware is that it doesn't only encrypt your files, but also it extorts you to pay the ransom. Let's see how. So first, the first step, when it encrypts your system or it infects the system, it provides you with a small note. The note includes the contact details of the attacker. Now, the contact details, as we all know, it doesn't include the phone number and the email address. It includes the only thing meaningful to the attacker, which is the Bitcoin address, in order for you to send the money to the attacker. Now, what happens next? The files, after the files are encrypted and the note is displayed to the user, what happens? We move on to the next step. The attacker keeps asking for the ransom, or it threatens to leak the data if no payment is made. So your files are not only encrypted or would only stay encrypted, but also will be leaked to the public. And of course, the ransom payment demanded continuously, and we will see also on the fourth step how the files are encrypted. We're going to perform the analysis using the IDA debugger. Usually we do the reverse engineering using Ghidra or GTB most of the time, but this time I would like to do it using the IDA. And of course, we're going to use the sample or the lab environment in the challenge under LetsDefend. So in LetsDefend, there is a section for challenges, and our challenge today is Ryzen ransomware. You can actually practice your reverse engineering skills by accessing this environment, and of course you can also do the questions. So we're gonna spawn the lab environment and do the analysis. So once we connect, I'm going to go to the challenge file. Here we can see the ransomware in a zipped format. Just right click, and maybe you can open it with the 7-zip file manager. And then we're going to extract this executable file. The password is infected. Okay, let's see. All right, next we can click on the tools folder, and here we can see multiple tools that assist for the analysis. We have the IDA, we have LSpy, we have Immunity Debugger, and of course we have Ghidra, and also DNS Spy. As I said earlier, let's do it this time using the IDA. Once IDA is opened, guess what's the next step? Next step is to analyze the file. So let's see where's the file. You can just drag and drop. Okay, we have a note here. Select portable executable, because this file is a portable executable, and click on OK. Couldn't find, you can ignore the warnings for now. And we have the file, we have the binary loaded. Now we can see this is the IDA view, or the graph view. In this tab, we can see the hexadecimal representation, the structures, and also for the static analysis, we can see the imports and the exports. On the right or on the left pane, we can see the functions. It's very important to understand how to navigate the functions. I'm going to explain how. And of course, we can control the graph view, and down here we have the output. All right, so what's the first step here? We can start directly with answering the questions, but I would like to give an overview of how to work while reverse engineering the files. Now, basically, the first thing we want to look at is the main function. You can see that this is the main function, right? Next, after taking a look at the main function, you can have a look at the function calls. Usually, when the target is a Windows operating system, the ransomware or the malware relies heavily on the Windows API calls. So it uses native Windows API calls to perform its job. Here we can see a function call to get process heap. So here it is trying to access the process memory. And if you scroll down, we can see other function calls such as create file, set file pointer. So here in Microsoft documentation, you can go to the main page. So let me show you the main page. So this page, this is the Windows API index. If you are stuck, you can just search for the function. For example, here we have the function name create file w. Just search for this function here. And we have multiple results. We can have a look at this one, create file w function. It highlights the name of the function. And we have a description here. It says creates or opens a file or input output device. So we know that. So now we know that this is a function call to create or open a file. Remember earlier we discussed or we talked about how the ransomware first creates a file that includes the contact details, right? Now, basically, this is it. Here, the ransomware starts by calling create file function to create a file name Risen or Ryzen logs. So basically, the Ryzen logs probably contains the ransom note or the contact details. Okay, we scroll down, we can see other function calls. We have create a mutex, and the mutex name is Ryzen mutex. So basically, mutexes are used to manage the resources of the process. It prevents the concurrent access or the simultaneous access to the resources of a specific process. Scrolling down, we can see sleep functions, and we have get count process. And look at this one, set process shutdown parameters, and we have get system default UI language. So basically, get system default UI language is a function used to retrieve the system UI language, right? Now, what happens next, we see multiple conditional jumps. It starts with a comparison, and then it moves next to a conditional jump. And we can see we have 1, 2, 3, 4, 5. We have 5 conditional jumps. What's happening here is that after the malware or the ransomware retrieves the system default language, it performs comparisons. And based on the comparison output here, it decides whether to do the jump. Here we can see multiple jumps. Why do we have 5 conditional jumps? We have 5 conditional jumps because the malware is trying to evade running in specific system languages. So first it retrieves the system language and then performs 5 different conditional jumps. Okay. And then lastly, let's do this, have a look here. The last one is a call to the function sub43cd0. So probably here the malware is trying to evade running on systems that have specific language codes or maybe located in specific countries. All right. Now, if you want to jump to a specific function in hand, or if you want to do that, you can go to jump and click on jump to function. For example, if I want to jump to the main function, I can use search, type main here, and I have the main function. Double click on this, and you will go back to the main function. All right. Let's go back now and see what are the questions. Which text file was opened by the malware after initializing a critical section? We saw that. We saw the answer actually. It was here. So using the create file Windows API call, the malware or the ransomware was able to create a text file called Ryzen logs. What is a mutex that was created by the malware? Again, we saw that earlier. Using create mutex API, we saw that the ransomware created a mutex with the name Ryzen mutex. How many countries or system languages does the malware prevent itself from running in? We also discussed this, and we saw that there are 5 conditional jumps, meaning 5 countries or 5 languages. What is the address of the get system info in hexadecimal? So we have a function we are interested in. So basically, we're going to copy this. We can have it over here. And we're going to search for the function. You can jump to function directly from here. Let's see. If you don't find it this way, using this method, you can use the text search. So we can use the view or the search and select text. Paste the function name, click on find all occurrences, and I click on OK. You can ignore this. All right, so we have all the occurrences of the function get system info. If you go here and have a look at what does this function do, okay, so get system info is a function that retrieves information about the current system. And this is the address of the function. And that's the answer. You can double click here to have a look at where the function is being called. Okay. What is the first API that resolved into the sub 403.120 function? Again, we are interested in analyzing a specific function. I'm going to copy the function name, and you can search for the function. Okay, now you can do this here. Search, text. And we have 2 occurrences or multiple occurrences. Or the way I prefer is this. We can go to the jump and I click on jump to function. Of course, you may not find it here, but it's always preferred to use this method. So search, paste in the function name, and here we have the function. Double click on this, and it takes you directly to the function. So what is the API? What was this? What is the first API that is resolved in the function? Let's have a look here. So I have multiple parameters declared. We have a couple of move and push instructions, exort encryption, and then we have push process name is WoW64 process. So this is the API. This is the Windows API, by the way. That's the answer. What is the scheduled task name created by the malware? Now, finding the answer to this question is quite a bit difficult without using the search, because here we want to find out. Let's go back to the main function. So we can jump first to function main. Okay, so as we said earlier, we want to find out the name of the scheduled task. This means we want to find out the exact command executed by the malware, right, to create the scheduled task. So the malware can either create the scheduled task itself or by using the native binary in Windows operating system responsible for creating scheduled tasks. Now the native binary name is scheduled task.exe. So basically you can use the search again and look for search scheduled tasks. Find the occurrences. You should find out if it was used. You can see multiple occurrences of this Windows or the native Windows tool. So this one highlights creating a task. Let's have a look at this one. And the function name, that's the function that creates the scheduled task. And we can see the scheduled task. When you hover over the mouse here, we can see the scheduled task name is system defense. So that's this task name. What is the array name that contains the volume used by the ransomware to encrypt the files? The array name that contains the volume used by the ransomware to encrypt files. So here, usually the ransomware accesses the file system by first enumerating the existing volumes. To do that, again, the ransomware needs to use the API calls. You're gonna have to find out what are the API calls used to retrieve the volumes and drives. You can go back here to Win32 and search for maybe get drive. Or maybe you can use the Google search, because we don't know the exact function name, and there are multiple function names that manage the disk drives. So let's use Google for this. Let's go back. So here the question is the array name that contains the volume used by the ransomware. So here Windows 32 API volume management functions. Let's have a look here. Okay, so we have get drive type determines whether a disk drive is removable, fixed, or a network drive. Get logical drives. So we have multiple ones, but which one is the one we want to look up? That's the question. Contains the volume used by the ransomware. All right, so let's use the text here, search, and maybe use get drive. So you can type the full function name, but for me, I'm going just to type get drive. Usually the function we are looking for starts with get drive or get volume. You see, all the functions, they have common naming convention. It starts with get volume or get drive. So we can use search for get drive and find all occurrences. We see here get drive type. Let's have a look at what does this function do. So we can use get drive type W. Determines whether a disk drive is removable, fixed, or network drive. Determine whether a disk drive. Okay, let's have a look at this call. So we have a call to get drive. Get drive type. Argument list is provided, and what is provided is this Q. So that's probably the drive letter, and that's the offset of the drive letter. Scrolling down, here you can see it starts to access the contents and the path names. So the drive we are looking for is Q. That's the drive letter. And this is the offset. What was the question? What is the array name that contains the volume? The array name that was used by the ransomware. So that's the array name actually. It's this one. And lastly, what is the Telegram username of the threat actor? Alright, so here the Telegram username should be included in the contact details that we saw earlier. Remember that the contact details were written on the text file, and the text file name that we discovered was Ryzen logs. So we want to find out the Telegram username. We want to access this file, but that's technically impossible now. What we want to do, we want to search, use the search again, and look for Telegram. And we have multiple occurrences. Let's have a look at this one. So it all starts using this function, and we can see multiple strings. We have an email address, and we have a Telegram username. You can double click on this, and you can see the full Telegram username. Now, in the last two parts of this video, we're going to complete the analysis. So basically, this is independent or not connected to the questions of this task or of the challenge. Okay. Now here, part of the ransomware analysis process is to find out the encryption key and to find out the file extension or the extension used to encrypt the files. These are two crucial components if you want to start the recovery process. For that reason, we're gonna now have to look at the C code, okay, using a program such as Ghidra. So here we can start a new project and name it as Ryzen. And here we can double click on the challenge file. I'm gonna have again to re-extract the file. All right. Drag and drop. Click on OK. And now the file is being imported. Let's see here. So we're going to click on OK. Click on yes to start the analysis. Analyze. Just wait for a couple of seconds till the analysis is complete. And next we're going to start the analysis. Now, since we know how the ransomware works and what are the main components, we're going to dive directly to the main idea. So the main idea here is to find the file extension that's used to encrypt the system files. To do that, again, we're going to have to search for function calls. Now, usually when the ransomware encrypts the files, it usually recreate the files or move the files to a new location with a new name. That's why we're going to have to search for a function, for a Windows API function that's used to rename files or to move files. One of the common popular functions is the move file. So you can here click on search and select program text. From here we can type in the function name, move file, select all fields and click on search. So we have a function named move file W. Probably gonna have to take a look at this one. Okay, so this is the function. As you can see, when you click on the function, we are taken directly to the C code in the decompiler. Let's have a look here. All right, so that's the complete function. Now the line we are interested in, if you scroll down, we can see that this is the function called move file W. So what it is moving, it's moving basically the old file. In order to encrypt the file, it's going to change its name. So here, the parameter _1, apparently it is the parameter used to hold the original file name. If you scroll up, you can see here it's actually using the parameter, and then that's how it is renaming the file name. So the old file name is used, and then the extension is changed to dot, and we can see the attacker's email address, underscore, comma, underscore, telegram name. This is probably a telegram name, and this is also concatenated with dot, and we have probably a variable to hold a random value. So that's the file extension. The file extension is a combination of the attacker's contact details dot a random identifier. Okay. Now, usually the file extension is actually apparent when you analyze a sample encrypted file, but it's very important to know how to find it using the decompiler. The next thing we want to do is to extract the encryption key. To do that, we can have to again search for a related function call used to encrypt files. So we can go back to search and use maybe encrypt, or just use crypt to find out all instances of all kind of functions used to perform encryption. So we select program database and we select the fields we want to search. So for me, I'm going to search the comments, the functions, and the labels. Click on search all. Okay, so in the results, we can see there are multiple functions that use encryption. We have these 5 functions. Scrolling down, we have crypto export key, as you can see here. So probably the encryption keys are exportable or they are meant to be exported. Crypto import key. Right, I think here we have a case of public key cryptography. So basically, probably the ransomware uses a pair of private and public keys. Let's have a look at this function. This function takes one parameter, parameter underscore one, and we have a couple of variable definitions. Then we have here the function appears to check a file for encryption. So first, if debugging is enabled, it logs is encrypt. So it checks if the file is encrypted or not. Probably the file is passed to parameter underscore one. The file to be encrypted is passed through this parameter. First, it is checked whether it was encrypted or not. And then we have set file attributes. It sets the file's attributes to specific state using this value. Probably this corresponds to the normal attribute. And then we have create file, opening the file and seeking a marker location here. When it opens the file path is given by the parameter here. We said that earlier. And then if we scroll down, let's see here. Now the file opens successfully, it uses set file pointer x here. So there's a if statement. If the file opens successfully, it uses the set file pointer x to move the file pointer relative to the end of the file. Here the offset used this value as a signed value, basically, which actually positions the pointer to 292 bytes probably. Okay, this is not important for the encryption key. Let's scroll down. We have this read file. So before reading, the code initializes the first few bytes of a buffer with a signature. It writes the characters R-I-S-E, rise, into a 4-byte variable, and then it sets the next 2 bytes to the value 4E. Okay. Which is the ASCII representation of the N. As you can see, the character here is N. So we have the full word Ryzen, the name of the ransomware. So together, these form the string Ryzen. All right, then it attempts to, as you can see, read 292 bytes from the file, starting from the calculated offset into this buffer. If the read was successful, the function calls another routine here. This is the other function, with part of the buffer here. Part of it is actually passed, likely to process or validate the marker data. Then we have cleaning up and logging. Okay, let's have a look at the function that's being called here. So we have 2 parameters passed to this function. First one, we learned that this is the file that's encrypted or being encrypted. And we have another parameter as well, variable declarations. And here we have a variable named UVR2 that holds this value. Probably this is the checksum value, if I'm not wrong. And then we have an iteration using while and do. Looks like a bit by bit processing. So for each byte here, we have 8 bit being processed in a loop. So with each iteration, what do we have with each iteration? We have first checking the least significant bit of the current checksum. And then if that bit is 1, it performs an XOR. We have XOR here, as you can see. So if it is 0, we have it just shifts the checksum to the right by 1 bit. This is all shifting the checksum by 1 to the right. And this is also repeated 8 times to incorporate the entire byte into the checksum. So after processing all the bytes, let's see here, the function returns the bitwise NOT of the checksum. So this is the bitwise NOT, the tilde, it is the bitwise NOT of the checksum. So probably this function just computes the standard checksum over a given memory block. All right, let's go back to the menu here. So we analyze this function, right? Okay. And now we move on to this function. So in this function, we have interesting things to talk about. All right, this one, we have parameter 1, parameter 2, 3, and 4. Remember that parameter 1 was used to hold the files to be encrypted, along with the keyword Ryzen, the name of the ransomware. And scrolling down, we have the log message generation key, and we have a couple of calls to crypto generate random, buffer declarations, buffer allocations, byte shifting operations. So here, scrolling back up, we can see that the function uses the provided cryptographic provider here. The cryptographic provider, this one. So it uses this one to generate 2 sets of random data, each one with 32 bytes long. One block is stored at offset 068, as we can see here, with a structure pointed by the parameter underscore 3. And the other one, or the other block, is stored at offset 048, as we can see here. Okay, scrolling down. All right, so here, look at this. We have a call to encrypt. So here it calls the function encrypt using the provided cryptographic key. Here, this one, parameter underscore 2, we talked about earlier. So it encrypts the data starting at the offset 6 here, right, of parameter 4, with the maximum buffer size equals to this value in hex, which is actually 256 bytes. So that's where the encryption process goes. But it's still the encryption key. It's not actually visible, not hard-coded. It is generated using a systemized mechanism. So it's not hard-coded. We're gonna have to we're gonna have to execute the ransomware ourselves and do the encryption process using, maybe you're gonna have to use GDB debugger, maybe to derive the key using this process if we follow the same logic. Okay, scrolling down. Now, lastly, this section is responsible for wiping out the data buffers. So here, all of this, it is actually zeroing out the 32 bytes, each at the offsets we mentioned earlier, the 68 and 48 within parameter 3. Yeah, actually, it does this to ensure that no sensitive material is left in memory. So also here, we cannot derive the key from the memory. The only way to derive the key is to do the encryption process ourselves. So we're gonna have to follow the same logic by executing the ransomware and maybe using GDB debugger. So at the end, the function generates here 2 blocks of random data. Use one of them along with the fixed ASCII string. The ASCII string can be derived from these values to construct a key expansion data structure, and then it copies parts of this structure into an output buffer. And then using the encrypt, it encrypts this output using a provided cryptographic key, denoted by the parameter underscore 2, and lastly, it cleans up the sensitive random data afterward. This is all, that's how we know what composes the encryption key. It's actually a couple of random data generated in memory, and lastly, after it is used, the random data is wiped out. So the only way to derive the encryption key, again, we're gonna have to execute this and monitor the memory. All right, moving on to other functions. Let's see. File is encrypted. Let's have a look at this one. So that's another function as well. Looks like this is the core file encryption routine. Okay, we have a couple of variable declarations. All right, scrolling down. Now we have, if debugging is enabled, it's going to log encrypt, and then it calls another function. That's another function to check if a file is already encrypted by looking for the Ryzen marker. So remember the Ryzen, the Ryzen keyword we discovered earlier, it's the marker used to figure out whether the file is encrypted. So using that marker, it's going to be able to find out if the file has been encrypted or has undergone the encryption process or not, using this comparison. And if it is encrypted, it's going to, if the Ryzen marker existed, it means that the file was encrypted before, and it's going to log the message file is encrypted. Okay, let's see. Also here we have buffer allocation. So we have allocates a large buffer value. This value is allocated for file data, and a smaller string buffer down here is also allocated. It will later be used probably for constructing file names. This value is used for file names. I mean, it's small comparing to this value. All right, scrolling down. So here, these lines, let's go over these lines. I have a while loop, and the function initializes a header structure with a fixed marker. We have another marker here. It's actually the same marker we saw earlier, Ryzen. It writes the characters rise and the character n at the end here. This forms the string Ryzen we saw earlier that serves as an indicator that the file has been encrypted. All right, next we have this one, cannot access file. Okay, we have this line. So here it opens the target file using create file API call with read-write access and stores the handle in parameter 1. Okay, it retrieves then the what looks to me as the file size. Okay, let me remove this from here. So the file size here is retrieved. If the file size is 0, or if the call fails, it's going to abort. It's going to abort. That's very clear from here. And the function logs an error. Cannot generate key for file get last error. All right, let's see here. Scrolling down. So this line, there's a function call. It calculates the CRC using this function on a buffer likely part of the header or key data for integrity reasons. It also copies a constant string. Okay, this is the string into a local buffer. This is the local buffer. All right. So all these lines are responsible for encrypting the file contents. Still, the key is not clear from here. It's actually being derived from a set of public and private keys that were generated randomly. Okay, we're gonna keep scrolling down until the encryption process is complete. All right, so here the handle is closed. Probably here the mark of the encryption process. That's where it ends. Okay, after the encryption process ends, probably here we should see the file name being changed. The function constructs here a new file name by taking the original name, okay, appending a suffix here that includes this character, right? And a string here looks like we said earlier that this is the email address and the Telegram username, and then closing it with the same character. Okay, we have two braces here. So it starts with one brace, and here we have the contact details, ends with this character, and then the extension is copied directly from this variable. And then it uses the call MoveFile W to do the rename process. If the rename fails, it's going to log this message. And of course, lastly, it removes and wipes out everything from memory so that no data is remained there in the memory. That's the objective of this function. So basically, it encrypts a given file. We saw that the given file is stored in the parameter _1, and then it uses the marker Ryzen to verify whether the file was encrypted before, and then generates a cryptographic key, and of course simultaneously it uses the Ryzen marker for the verification process. And we saw that the encryption process is actually it goes in chunks depending on the file size. And lastly, that the encryption process is complete, we saw that the extension of the ransomware, let's scroll down, it's too long. We saw that these lines are responsible for the choosing the naming convention of the encrypted file. That includes the attacker address, email, and Telegram username. Now this variable, if we inspect this variable, let's have a look. Probably this variable includes an onion address. Gonna have to check. Okay, this is the variable. This variable forms part of the extension, and that's where it's referenced in these three functions. Again, to derive to extract all of these missing parts that we couldn't find here by analyzing the code, we're gonna have to execute the ransomware using GDB debugger and debug in real time to extract the encryption key. All right, so that was the full analysis of this ransomware.